Summers in Miami can be hot. I'm told the humidity makes it feel hotter. Why is this?
Excellent question, LeBron. Let's first think about what people are talking about when they even say humidity. And there's a couple of ways to think about humidity, but typically when you hear the weatherman or in everyday talk, people say, hey, it's really humid out there, or it's really high humidity. They're talking about relative. They're talking about relative humidity, and it's usually indicated by a percentage. And let's just think about what the different percentages of relative humidity mean. So right over here, we'd have 0%. Let me mark it like this. So here we'd have 0% relative humidity. And over at the extreme other end, you have 100% relative humidity. And at any given point, the air is someplace between 0% humidity and 100% relative humidity. At 0% relative humidity, it's essentially saying that there's no water vapor in the air, or a non-measurable amount of water vapor in the air. And so if we go to this molecular view of what might look like a little water droplet maybe on the surface of our skin, so just to be clear, these are skin molecules, not even skin cells. These are the actual skin molecules. I just simplified them as brown circles. And this right over here, this is the actual, these are actual water molecules. So these are water molecules. And maybe it's a drop of sweat or a little water that got dropped on our skin, and it's in its liquid state. And in the liquid state, you have these hydrogen bonds between the molecules that aren't super strong, so it allows these molecules to slide past each other, and that's why liquid flows the way it does. And we've already talked about why sweat makes you cooler, but we'll review it a little bit. Whenever we talk about the temperature of something, we're actually talking about the average kinetic energy, or the average motional energy of the molecules that make up that thing. But it's the average. On an individual molecular basis, they could have very different kinetic energies. This molecule right here might be going really fast in that direction. This molecule might be going slower in that direction. This molecule might be going super fast in that direction. This molecule going in this direction. And when we talk about the temperature of this water, we're just talking about the average kinetic energy. Some of this molecule might be rotating really fast that way. This one might be rotating that way. This one might be vibrating with a certain kinetic energy. And so sweating, what it does for us is, if let's say my skin molecules, they have some temperature associated with it. So these are all vibrating and bumping into each other to a certain degree. And then they will vibrate and add kinetic energy. They'll bump into these water molecules, and these water molecules will bump into each other. And what happens with the water molecules is the ones that have a really high kinetic energy have a higher chance of escaping the bonds with the other water molecules. So for example, maybe this one has a really high kinetic energy and it's in the exact right direction. And so it's going to go really fast in that direction. And it has enough kinetic energy to essentially escape this attraction with the other water molecules. And so it enters a gaseous state. It essentially becomes water vapor. It just gets mixed with the rest of the air. And so when you have 0% humidity, you have no water vapor up here. It's very easy for something to do this. It's very easy for it to escape. Maybe this one too is about to escape in that direction. And as we already talked about, when you have your things with the highest kinetic energy leaving a system, then your average temperature for the system is going to go down. You're losing the things that I guess you could say are the hottest, that have the highest kinetic energy. So at this state right over here, evaporation is very easy. Easy evaporation. Or you could even say easy evaporative cooling. So at 0% humidity, you can sweat very efficiently. It really cools you down. Evaporation. Easy evaporation at 0%. But as you have more and more water vapor here, we go up this humidity scale. So let's say we start having a little bit more water vapor in the air. So that's some water vapor in the air. As you have more and more water vapor in the air, you still have molecules that can leave, but now you have some probability that some molecules in the air might actually condense and become part of the water again. So you still might have some net evaporation, but it's not going to be as much, because you could have some water vapor that gets captured by these water molecules, and so the rate of evaporation is going to slow down. All the way that you get to 100% relative humidity. At 100% relative humidity, and it depends, the actual amount of water vapor depends on the temperature and on the pressures we're dealing with. But at 100% relative humidity, you have so much water vapor. You have so much water vapor that it is possible still it is still possible that some of your liquid water might have enough kinetic energy to escape, but you're just as likely to have water vapor condense. You have so much in the atmosphere that for as much as this is evaporating, you have other water vapor that is condensing. You have water vapor that starts to get, I guess you could say, captured by your water drop. Gets captured by your water drop. So at this point, at 100%, you have no net evaporation. The air is saturated. No net evaporation. So at that point, having sweat is useless. You're having no net evaporation. You're not able to take away your high energy particles. And so the cooling down that you normally do for sweating is no longer in effect. And we see that here in this chart from the National Weather Service. They give the heat index. If the real temperature is, let's say the real temperature is 90 degrees, we see as we have higher and higher relative humidities, they're starting at 40% relative humidity, because that's just when you just begin to start to notice it, all the way to 100%, the effective temperature, what it feels like, it goes all the way to 132 degrees, or it feels like 132 degrees. And this is important because the body isn't cooling it. It's not just a perception thing. It also can affect your health because the body can't cool itself down anymore. It can't dissipate it can't dissipate heat through the traditional process of evaporative cooling.